Welcome to today's webinar on the topic of science gateways. Science gateways have emerged as a very successful way to enhance collaboration and impact software development, databases, and computation by providing an online portal that can be used for training, engagement, and to reduce the barriers for people to use computer resources that are accessible throughout the country. And so I'm very pleased today to introduce Dr. Sudhakar Pamidighantam from Indiana University. Sudhakar has been a research scientist for high-performance computing and applications at the National Center for Supercomputing Applications, NCSA, at the University of Illinois for the last 25 years. And he's been developing and deploying production cyber infrastructure for chemistry and computational biology communities supported by the NSF. And so today he's going to provide an overview of the cyber infrastructure for science gateways. So please take it away, Sudhakar.
Thanks very much. For the introduction. And so in this presentation, as Aurora was saying, I'm going to talk about what we call cyber infrastructure for science gateways. So I represent a couple of communities here at Indiana University. I'm at a cyber infrastructure integration research center that has been formed recently. So we used to be called Science Gateways Research Center before that. And also I represent XSEDE, which is the Extreme Science and Engineering Discovery Environments, which is an NSF funded project that brings many compute resources together for the community. I think I also should probably, and probably some of these I think are mentioned, in this presentation, but also I'll just say that I also represent Science Gateways Communities Institute, is one of the two institutes that NSF funded a couple of years ago. This one particularly to engage scientific community with science gateways, development communities. So the outline for this is, again, I think is not AMP gateway, as I was saying here. Sorry about that. So this is what is cyber infrastructure, what are the services that are needed for this, and what kind of core software that we use for this presentation. So AMP is another gateway that where we deployed. There may be some references to AMP Gateway and Delta, which is the project that NSF funded recently, which we are trying to create a science gateway for. So cyber infrastructure in general is kind of defined as follows. It is to integrate local and national resources, data, databases, compute, network, and storage resources to enable science to happen, particularly simulational science, on these supercomputers from the desktop environment smoothly. That means a single stop for accessing multiple applications on multiple resources, and so on. So some of these NSF funded supercomputers include Blue Waters and Frontera recently. Both are what are called class 1 supercomputers with large number of nodes and large number of cores together. And XSEDE, which represents, again, different supercomputer centers that host these supercomputers. The NSF cyber infrastructure vision 21 contained an organization that brings together many NSF funding activities together. So they include instruments that contain telescopes, spectrophotometers, X-ray instruments, and so on and so forth. And various organizations, institutions like universities, government labs, and non-governmental agencies with institutes like XSEDE, which create software that can allocate all these resources in a uniform manner, and then provide expertise in terms of extended collaborative support services, experts in optimization, experts in science gateways, and so on and so forth. And then, of course, broadly provide computational resources, software, both application-specific software as well as generalized math libraries and other general software. And so, of course, this requires a networking to bring all these resources and institutions and organizations together. And of course, data is becoming more and more important, and there are a lot of public level databases, and a lot of these projects also require hosting a model data at a HPC center, and biological databases, structural databases, and so on and so forth that need to be hosted and accessed and smoothly integrated with all the discovery process, including simulation and analysis. So XSEDE also provides these large supercomputers, as I was saying, and they have programs called campus bridging that brings together local resources or campus resources and personal resources like laptops and desktops in a uniform way to access both local as well as national level resources. So the XSEDE resource pool contains this list of supercomputers that are hosted at different centers. For example, there are Jetstream at Indiana University. There is a Maverick at TAC. There's an LSU supercomputer at LSU. PSC hosts Bridges and some storage system called Pylon. San Diego Supercomputer Center hosts Comet and a big disk called Data Oasis. And TAC and IU together were hosting this Wrangler data hosting system, which was recently retired, but IU continues to support that. And of course, Ranch is a storage system. So this is the NSF compute resource kind of roadmap. So we have recently seen Frontera deployed at Texas Advanced Computer Center. So Jetstream, Bridges, and Comet are still serving the communities ongoing fashion. So Blue Waters, which was a class 1 supercomputer that was hosted at University of Illinois, is, I think, has been extended, I think, to go through this summer in 2020. So, of course, networking also is important to bring international communities together. We have several projects. XSEDE interacts with European consortium and even Eastern European and Middle Eastern supercomputer centers like the Cyprus Center, and and even in Australia and New Zealand. So these networks provide access at a very high level between international supercomputer systems. So the pathway for discovery then is envisioned to involve discipline-specific and domain-specific environments like these gateways that can use integrative middleware, like Apache Airavata, Agave, and NanoHub, Hub Zero, and things like that, to enable the science workflows to be executed on various kinds of hardware platforms, like NSF-supported supercomputers, as we have listed, but also local and private commercial clouds, and even international systems. And of course, this is it depends on the cyber infrastructure that NSF funds and the networks and so on. So this is supposed to corroborate measurements and then be predictive and provide a new science for the benefit of the community. So science gateways, coming to the gateways themselves, are web and web-based interfaces. They could be web browser or desktop interfaces that exploit the middleware, which is the software that provides programmatic interfaces to be the go-between between the users, the research scientists, and modelers, and the devices, high-performance supercomputers, and so on and so forth, by bringing together data, computing, expertise, and so on and so forth. And of course, this has to be done, securely and consistently across the board. That means that if some data needs to be proprietary, it has to be kept proprietary. If a data need to be shared, then the infrastructure needs to provide a capability to share the data among many users. So this slide just compares two scenarios. On the left, there is what is called a command line type interface, just a terminal where people use standard protocols for secure login and use this command line. So on the right, there is a graphical tool that can enable users to create inputs and prepare inputs for a particular application, and then execute the application on a remote resource. So the difference is that the complexities in command line interface in terms of the knowledge required to log into a particular resource and know about the resource capabilities, and the process through which some simulation has to be started in some kind of a scheduler systems, is all abstracted in these gateways. So of course, this is very, very specific to a Delta gateway. So typically, science gateways like the Delta gateway also require an allocation on these supercomputing systems. So this suggests that an allocation is obtained for the Delta here, and a gateway need to be hosted. Some kind of a community login maybe required as part of the allocation, and the gateway needs to be deployed by some hosting service. And so these are kind of some generic requirements for any gateway to be hosted. Of course, in this case, we say that a large amount of disk based storage system is also attached to some of these devices, so that simulation data can be stored and reused for simulations or analysis. So continuing this, the definition of what a science gateway is, as I already alluded to, web and desktop interfaces to high performance computers and clouds. The gateway encodes expertise in terms of executing simulations and workflows, moving data to the right place where it is needed, and providing tools for pre and post processing. And it brings communities to the resources and brings resources to the communities. And it would enable sharing the results and be able to easily recover a simulation and reproduce if needed, or modify and repurpose a particular simulation with different data, different resources and requirements. Of course, these gateways are built using what I refer to as a middleware. So the middleware is the box in the middle here that provides many of the functions that when they are functioning correctly, I mean, the user won't even notice. But this is quite important that a robust middleware is available to enable this discovery process in the science gateways. So some of these functions are described here. Of course, this particular middleware refers to some specific functions in a particular middleware software called Apache Airavata, which is an Apache Software Foundation software. But many gateway middleware architectures would contain these basic functionalities. So one of the functionalities, an identity authentication mechanism through some kind of an identity provider to authenticate users coming into the gateway and then securely provide access to the resources, software as well as hardware resources, and account for the usage of these resources. This authentication also provides a way down the line to authorize a specific authenticated user with a specific software or a hardware or a combination of those. So different kinds of communities can be supported by these middleware systems. In the case of Apache Airavata, it can support multiple gateways that serve totally different communities from different domains. For example, we have a Delta gateway which supports topological analysis of molecular sciences data. We have gateways that I refer to AMP, which is atomic and molecular physics gateway. We have gateways for library sciences and so on and so forth. So different kinds of communities can be simultaneously supported through a single instance of this middleware. So the middleware also provides a way to generate user interfaces for users to engage with their application of interest. For example, for chemists, we have molecular viewers and editors and so on and so forth. For library sciences, it could be just a way to get text into the for text mining purposes, text from URLs and on the web and so on. So each community may have their own specific user interfaces, but also there could be some generic user interfaces that abstract simple input and output for an application. So there is, of course, the user management and security policies that the middleware need to support. It need to support execution of an application on remote resources, including clouds, in an organized and secure manner. And these execution engines need to scale to a large number of experiments that are submitted simultaneously by a large community in a particular gateway. And there may be multiple gateways. So the execution engine needs to scale to the level that it can be supported. So there are services that can elastically grow or shrink depending on the need in these execution engines. And all this process need to be cataloged, and so there is a monitoring of these processes. There are messages that need to go back and forth between these compute resources back to the user. And of course, the gateway needs to manage all these information services as well. And there could be pre and post processing of data that may happen as part of this execution of a workflow. And if the workflow need to be restarted, one has to be able to know the provenance of the workflow and extract all this data, and that so that kind of a provenance gathering needs to happen in the gateway, and the cataloging the process is very, very important. And in the case of post processing, I mean, there could be additional protocols that need to be supported by the gateway middleware to enable either automated post processing for some streaming data or explicit data post processing. So I mean, again, just a couple of information bullets here for Apache Airavata. It is an open source, open community software managed at the Apache Software Foundation. I mean, it goes through Apache model, and it is open. So there is something called meritocracy here, where people who contribute becomes the owners of the software, and not necessarily the people who actually originally deposited or donated the initial versions. So the software is a multi-tenanted software that supports scientific workflows on supercomputers in general. So some of the gateways that Apache Airavata was supporting are listed here, and some brief description. So UltraScan is a gateway that supports ultracentrifugation experiments and corroboration by simulations. GeoGateway is a NASA-supported gateway for earthquake modeling. SimCCS gateway is a gateway from actually between Indiana University and Los Alamos National Labs to model carbon sequestration economics by optimizing the pipeline networks that push carbon dioxide into the earth. University of Dakota Gateway is a campus gateway that supports campus faculty, staff, and students using their own campus resource, simultaneously engaging them also with XSEDE supported national NSF supported Cyberinfrastructures through a program called Campus Champion Allocations. So DREG is a gateway for transcriptional regulational element analysis. SEAGrid is a computational chemistry gateway that I'm a PI of, and have been running this for about 15 years now. There may be some information about that. And Future Water Indiana is a geographic and a temporal modeling of climate impact on water resources in Indiana. So on the bottom, I have listed a URL for our group, and that this particular link provides a bigger list of collaborating gateways. So some other functionality that the middleware provides is listed here, and the technologies that it integrates. Again, Apache Airavata is a continuously evolving middleware system, which uses the best of the breed, well-supported community infrastructures, which is always better than just discovering and doing things in isolation by a particular middleware infrastructure. For example, we use a Django framework. Django is a web development framework. Is in Python, and then it can integrate JavaScript very easily, and Python type plugins quite easily, and that's what we choose to adopt. For so we have our own credential store for securing credentials to for communications between many systems. So even this credential store, we are looking for outsourcing to an open credential store type system. Keycloak is an authentication or identity management system that provides authentication and group-based authorization. Keycloak is pioneered by Red Hat, and we adopted that system for identity management. Tusk.io is a reliable file transfer system. We use this for transferring large files through the gateway in a reliable and restartable fashion. So of course, Apache Airavata natively provides application software and data catalogs. So this application and data catalogs are critical, particularly when workflows which stitch together multiple applications and maybe multiple data resources together. And the registration that Airavata use is quite generic and is being adopted by others. The sharing and publication services Airavata provides, we try to use some open software like co-manage, but we found that some of them are too heavy, and we peeled back, and we have our own sharing adaptation here. So we of course use internal and external user interface integration through desktop and web interfaces. I'll show some examples of this briefly. Of course, we use Apache Helix for execution engine to orchestrate workflows, for a single job as well as concatenated jobs. So we have a specific task monitoring and messaging service system. As part of this, we may actually use some email monitoring system from emails that come from schedulers. We also adopted Docker-based post-processing, and there is actually more happening in this space where we are trying to also provide a Docker support for application deployment as well. So this, so the Django, as I said, is a web framework. Here I'm just giving some briefly, how a Django portal looks like. So this view graph shows how creating an experiment is done through this Django web framework. So this provides a way to upload input files and then select a resource for the simulation and provide some job specifications in terms of nodes and course and time and so on and so forth. So the Django framework talks to the Apache Airavata API through some REST API calls, and so this is through a Python Airavata Python client, and it exposes these user interfaces onto the web browser. So web browser is what the user sees, and the Django and Airavata are completely hidden, and the references to the compute resources where the simulations occur become visible at the user interface, as you have seen. So the Django, as I said, provides a very rich way to interface with third-party components, user input components. For example, on the left, I show a map, which is from the SimCCS gateway. It shows some carbon dioxide sources and sinks that are on a geographic map, and the scientists can choose certain sources and certain sinks, and then start a simulation to optimize a pipeline network from the sources to the sinks. On the right, I show a molecule viewer that can be integrated through these Django type frameworks. So I mentioned about the execution engine. So we use again a third-party open community Apache Helix task execution framework. And so this Helix framework can be scaled to a large number of executions or shrunk to a few executions. And it is automatically done through some microservices. And of course, this view graph provides a detailed view of, how Helix takes a workflow and launches commands and uses messages going back and forth between the source of the workflow, which is the gateway, and the consumer of the workflow, which is on the other end at the supercomputer center. So I mentioned group-based authorization. Authorizations can be defined by by roles. There are users of certain privileges, and there are administrators with slightly different privileges, and there could be groups of users that can have certain specific privileges for access to certain resources, hardware, software, and data, and that can be managed through this group-based authorization. So just to summarize the middleware, the gateway middleware, it provides many functions that are useful for bringing together hardware, software, applications, data, systems, and user communities into a platform. And it provides these functions, and it's an open community software at Apache Foundation. So people can look at what the software does and contribute back if there is a function that is lacking and is desired by a community. And of course, we both at Indiana University and Apache Airavata, as a community software in general, works to educate and train, both in students and staff through various kinds of development opportunities. Particularly Google's Summer of Code is one of them. Capstone projects, and so on and so forth, and also the students from locally at Indiana University who take these classes do also contribute through these efforts. So I mentioned that I'm a PI of one of these science gateways. So here we'll see some examples of how a gateway is used in production. So SEAGrid is an Apache Airavata powered computational chemistry and engineering applications software, a gateway. So these gateways, used to be called grids. When the grids became out of fashion, I think now people have started calling them portals and gateways, and so on and so forth. So grid was originally coined based on the power grid. That is like I mean, you can plug an appliance into the grid, and then a lot of things are smoothened by the grid, like what kind of power is drawn, and what application needs to use that power and how. And so, so this is what the grid is about. So this was, I think, some data that was maybe last year's data about the SEAGrid gateway. So it's been running about 12 years, and I mentioned 15, where there was some development effort, I think, for the first few years there. But it has been consistently serving a large community of users, about 1,000, 1,100 users for 2019, by serving a large amount of allocation. These allocations are now counted in terms of actual, kind of dollars. The dollar figures are provided when we get an allocation. And this gateway was providing large set of applications, mostly chemistry applications, and people who use these gateways, are active in research, and they publish. And as I was saying, these gateways provide various kinds of user interfaces. SEAGrid was originally providing a desktop client, because these desktop clients have additional advantages over the web browser to interact with locally deployed applications and data, and so on and so forth, with much less security issues. Of course, the Django framework that I mentioned is all on web browser, and we are trying to translate whatever is doable on the desktop in the browser itself. So these browser-based tools are more recent. So we provide various kinds of services, workflow capabilities, checkpoint and reuse, high throughput and coupled application execution. And we provide this community allocation, which is like a block grant that is usable by community if they don't have their own allocation. But also these gateways support scientists' own allocations at national supercomputer centers like XSEDE centers, as well as DOE. And we also do consulting both in terms of deploying certain services in the gateway, or adopting new requirements, and providing also scientific consulting. So there are some quickly some view graphs here about how a gateway administrator manages users and applications in this case, and how resources are enabled in a gateway is shown here. So on the left, you see various resources, like Big 2, Bridges, Carbonate, Comet, and Deadstream, and so on and so forth. And for a given resource on the right, like Stampede 2, how a community access is provided through a community login, a particular project allocation ID to charge the simulation time, and scratch locations on the queues that are enabled. And some application interfaces are described here. So this shows so what we call a cascading input as part of the input preparation for an application. I mean, this is an application for a geochemistry gateway. And this cascading inputs is like, once you choose a particular option, like in this case, a one-phase region for the solvent phase, additional choices then become available, and so on and so forth. So if you choose, for example, instead of one phase region, the liquid vapor saturation curve, there will be alternate choices that can be configured, and this configuration is done through a JSON-based metadata modification scheme that is very straightforward to implement through an application interface development. I mean, so on the left, I show a development part. On the right is the result of this development that the user sees when they access this application. So the application deployment and a particular resource needs to define what the application is. Again, these applications can be just executables that are compiled, or they could be wrapped. In this case, I'm showing this run G16 with checkpoint recovery, which is actually a shell script that wraps a Gaussian version 16 on a resource called comment. And various environments that are required for executing this application can be provided. And of course, there are other pre and post processing commands can be added to this execution. So a small workflow can be kind of embedded in such wrapping in a dynamic fashion. Of course, this dynamism currently is kind of restricted to administrators for a gateway. But of course, this can be opened up for development purposes to all users as well. So the other one is to monitor what is happening on the gateway through this what we call the experiment statistics panel here. For example, this panel shows for a given time frame between a couple of weeks in November 2019, how many jobs ran, how many completed, and how many failed. And we can pick one of these and dig deeper into more details. For example, if there are some jobs failed, we can see if these failures are due to a particular systemic problem on the gateway, or an input error, or things like that. And so this shows again an experiment creation for the same supercrit VL, the geochemical gateway application. And of course, this application runs on a cloud resource called Jetstream Cloud that is hosted in Indiana. So again, once the input is provided and some resource specific requirements are given, then this job can be launched and it starts to run. And this shows when the job starts to run and how it is monitored. Of course, this monitoring happens automatically once the job is submitted. That means a browser is refreshed and continues to refresh until the job completes. And in this case, the job completed and the outputs are presented right on top for the user to extract the outputs. So, I mean, there is a way to, of course, if, people won't submit just one job and wait. Users submit many jobs, and these jobs are listed through this, browse experiments facility. So they can also, once they pick up a job, they can clone this job and rerun it with different parameters or in a different resource, or restart a calculation in case something is incomplete. So this view graph shows that workflows can be enabled through these gateways. So this view graph shows a lamps-based X-ray diffraction coupling based on some MD simulation and extracting the data to run X-ray diffraction profiles and visualization of the profile at the end, like this reciprocal map. The one on the right shows that the workflow actually ran on multiple resources. So that means that after a task is completed, data is transferred to a different resource, and both are in XSEDE supported systems here. And then output is presented back to the user. So on the left bottom, the workflow, the same workflow is completed within Texas Advanced Computer Center resources. So there was a reason why this may need to be done originally on multiple resources. And the reason being, there are certain resources that can provide large memory. And then, of course, this large memory requirement was was removed once some optimization of this application took place during what we call an extended collaborative support project that is, of course, funded by the XSEDE as part of its allocation. And these collaboration projects provide expertise for optimization of the codes, optimal use of resources, and enhanced workflows, and hopefully better science. So this is just another workflow, again combining Tinker, which is a molecular mechanics application software that was used to do molecular mechanics of a calcium carbonate water cluster. And in series of steps, it was, some parts of this configuration were chosen to engage a higher level theory, and so on and so forth in this workflow. So finally, I think we also engage post-processing type frameworks in the gateway itself. So on the top level, you see that the flow is just launching simulations and then getting results. And the results are stored back in a gateway defined storage. Once the results are stored in the storage, another process can pick up the data and parse the data and automatically index the parsed data and provide an interface for searching and just visualizing the data. And this is the same process that is actually described here in more detail. But the data that is parsed is presented in this kind of a user interface. So this is again an example in the SEAGrid data portal. Several experiments can be searched or sorted based on certain criteria, and a detailed indexed key value pairs that are extracted from the parsing can be presented in this kind of a view. And eventually, of course, multiple experiments can be compared. So so finally, so what I would like to say is that these infrastructures are available, funded, and well supported. Of course, these need to be sustained. So this the sustained operations may require maybe additional funding, but some initial funding is available through XSEDE and Science Gateways Communities Institute's EDS activities. And the CIRC, the Cyberinfrastructure Integration Research Center at Indiana University, is deeply engaged in many of these activities, and we are here to help any requirements that any scientific community may need for their science. So I'll stop here and take any questions if there are. Thank you.
Excellent. Thank you very much, Sudhakar. Are there any questions from the audience at all?
I have a quick questions. Can user ask to install a specific software?
Yes. The users, okay, if it is a web browser based thing, the user doesn't need to install anything except their own application on a remote HPC system. And even that can be handled by these consulting services. I mean, if you have an application, I mean, a consultant can pick up the application and deploy them.
Okay.
So, for the desktop, there is probably a desktop application software that need to be downloaded and installed on the desktop.
Yeah, but my question is, suppose I'm using some specific statistical software, but I want to use the software in this center or this system. Then system has the software right now. Then can I ask administrator to install the specific software or not?
Yeah. So I mean, you can. So there are different kinds of mechanisms for providing software. In the XSEDE, there is a group called Community Software Support Group. If it is an open and easily obtainable software, like for example, R is a statistical software, or SPSS is a software. It is probably not free, but it is there is a license for things. So you can request, and depending on the funding they have, they may provide the software for you on their system. If it is an open source and it's free, it is easy because there is no cost, there is no licensing fee. If there is a license requirement, then if the center has funds to support that particular license, then they may actually provide that for you as well as to the other users in the community. If they don't have funds, then they may come back and say, whether you can support part of the license. And we have deployed some license software through these gateways, and we can couple a local license server. For example, if you have a license server at your institution, that can be used to support the software on XSEDE resources that can be supported.
Okay, thank you.
Thanks.
And so in general, Sudhakar, it seems as though kind of anyone who's interested in exploring how to create a gateway, first they have to have some kind of computational resources that they would be having software or that they would be doing computations with, whether it's the cloud or a local resource or XSEDE resources, right? And then the gateway, the gateway construction and the support for a gateway, whether it's through the Science Gateways Community Institute or some other resource like your CERC at Indiana, they're working with the providers of those resources, right, to be able to be integrated so that you have the gateway integrated with whatever platform you're going to be running your calculations on, right? So they're kind of two separate issues in some sense, aren't they? Whether how you have your computing resources, whether they're on AWS or XSEDE or something, that's a bit separate from the setting up of the gateway itself, correct?
Yes, I mean, so that there are separate processes. But if you have, let us say, some software that only runs on your laptop and no resources, so these services can also help you get to those resources. I mean, for example, you can start with a simple startup allocation on XSEDE that will provide immediately a resource. I mean, the startup allocation takes a week or less to get, and that process can start, and the consultants or in collaboration with the users can deploy the application that has no other host other than a local implementation. And it can start providing both the deployment of the software on these resources, I mean, also maybe find what is an appropriate resource for this application. For example, if you have a local application that uses GPUs, then we can find a GPU containing resource to deploy this application. And you can also optimize this application on that particular resource. And independently, there is, of course, this gateway development is a kind of an independent process that, of course, has this as a prerequisite. That means an application should be, there should be an application, and then it should have a place to run.
Beautiful. Excellent. Well, thank you very much. This was very helpful. Let's, you guys